Thank you. I was honored to be invited, and I'm even more honored now that I saw how many interesting people are here and different directions. My talk is not exactly designed for you. I'm going to present a paper that I wrote with my friend Al Roth that was going to appear in PNAS. Was really written to present an alternative approach to mainstream behavioral economics. So I'm going to review what we know about mainstream behavioral economics, and which is really popular nowadays. So it's written for the general public, but the general public knows behavioral economics nowadays. So it's really an important, influential field. But we think that there is some problem in that field. And I have to admit that the problem that I'm going to present, maybe many of you already thought of, and maybe already worked on them more than I did. So it's a little bit funny group to present it to, but I will try to present it as if it's a regular group, and you guys will not be in front. And don't get upset if you already, some of my ideas you probably wrote about 20 years ago. And I will be happy to get this kind of feedback. Okay, so my interest in this field comes when I was recently invited to give a talk for the general Technion student. By the way, I'm a psychologist by education, and I'm now at the Technion, also in Warwick University. I was invited to give a talk to a general course for Technion student on inventions and discoveries that have changed human civilization. And Technion is mostly engineering and natural science, and I was one of the first social scientists. And I said I'm going to try to make an effort to say how we social scientists affected civilization. And initially I had a hard time, but then luckily I drink enough coffee with my friend Al Roth, who tell me what good thing we social scientists did. And in particular, Al convinced me that there was really important inventions by social scientists that is almost as important as a wheel. And the most important one probably was trading. Probably one thing that distinguishes human from other animal is the fact that we are good in trading. So when you see your neighbor, well, let's think about 20,000 years, many years ago. I'm not sure when it's happened, but maybe 50,000 years ago, when you saw your neighbor being successful in hunting and you failed, probably the best strategy was to come behind him without him noticing, trying to kill him and steal the game. But then somehow some early social scientists invented the idea of trade. And instead of killing the neighbor, if it was a really big animal, say, if you give me a piece, I will give you some of the berries that I was able to pick, and I don't have to kill you, you don't have to kill me, we are both happy. So that was a good idea. And then this idea was improved by markets, law enforcement, firms, banks, auction, and now my favorite idea, at least in Israel, it's a big thing, Get Taxi. Get Taxi is a smartphone application that brings taxi, and this probably, from all the effort was done to reduce pollution in Israel, this is actually going to have an effect. Because nowadays, when you go to a restaurant in Tel Aviv, you don't going to drive. Faster, cheaper to take a taxi, just by this one application. One thing is common to all these ideas, and of course my friend Al Roth got the Nobel Prize for his contribution to matching. One thing is common to all these ideas, including matching, that these are all methods to reduce conflict under the assumption that people more or less maximize expected return. So the reason why nowadays I don't drive when I go to a restaurant in Tel Aviv is because it is cheaper and faster to get taxi. And the reason why I don't kill my neighbor, because it's better to go to the supermarket and buy stuff instead of trying to rob me. So these are good ideas, and most of them are just based on the simple ideas that people maximize. So I did that, I explained that to the engineering students, they were impressed. Say, yeah, I didn't think you social scientists did anything important, but actually you did. These are good ideas. And then I thought, well, I should also tell them something about the discoveries. And I looked at most interesting discoveries that I could tell engineers, and I found the St. Petersburg paradox, the Ale paradox, Kalman-Tversky, Dan Ariely. And what is common to all of them that they're all deviation from maximization. So I noticed there is some gap here. from one hand, all the important inventions are based more or less on the maximization assumption. On the other hand, all the cute phenomena that it's fun to teach students are about deviation from maximization. And something is wrong here. And the question is how to address it. Now, leading social scientists already noticed this gap. And I think the way they tried to solve that, starting with Bernoulli, was to say, well, people don't exactly maximize, but they do something similar to maximization. So basically, they come up with adding some parameter to the maximization assumption to capture the phenomena. So Bernoulli was the first to introduce this parameter for diminishing sensitivity or risk aversion to expected value theory to make it expected utility theory. Then some smart people provide axiom for that. And then other people like Kalman and Tversky here propose slightly different models that have 5 parameters. But it's also a generalization of the expected value. And this was a method that was very popular and highly popular in behavioral economics. This, people wrote bestseller books about this kind of stuff. Some of my best friends, Dan Ariely, I admire him. If I could write like him, I would write a book like that. But because I cannot write as well as these guys, we try to clarify the value of a different approach, which I think many of you already are taking this approach. So when I say a different approach, this is for mainstream behavioral economists. I understand that some of you already thought about it a long time ago. And the approach that Al and I are trying to present in that paper, instead of adding a weak assumption to the maximization, adding parameters to create some weak maximization assumption, that is having a decision-making model that is similar to maximization but not exactly, we gave up the idea of having a general decision-making model that is almost maximization, but we tried to come up with a learning model. And basically what we tried to do is to clarify the condition under which learning leads to maximization. So the solution we want to propose to this invention discoveries paradox is that maybe the successful inventions works because they create an environment that facilitates learning to maximize. So they don't really only assume maximization, they create an environment under which maximization holds. So it's really an engineering approach. This is of course what Al Ross got the Nobel Prize for, the engineering approach to economics. So the idea is that we create a mechanism under which economic theory works. In this mechanism, we not have to assume that it works everywhere. But if I'm the entrepreneur who comes up with the idea of get taxi, I create an environment that now people learn faster to use my system and make me rich and also make the environment a better place. So this is a basic idea. So if we understand how people learn from experience, then this solves the paradox. But this is what we have to do. We have to learn to try to improve understanding, not how people deviate from maximization. That's we can do if we want to write bestseller books. But if we want to help create a better world, it's important to understand when people do learn. And what I want to do today is to review what I think are the most important facts that we know about human learning. And we use this very simple experimental paradigm to do that. Basically what we did actually in this paradigm was to replicate all the old animal learning literature. With this paradigm, and the replication clarifies some of the phenomena. So basically in our experiment, the subject comes to the lab and being told the following. The core experiments include many trials. Your task in each of the trials to click one of the 2 keys. After the subject clicks, he gets a payoff for that particular trial. And his payoff in the end of the experiment is shop fee plus the payoff from one randomly selected trial. So for example, the subject can click on the right, and then he gets the following feedback. You selected right, your payoff in this trial is 1. In this experiment, he also told, had you selected left, your payoff would be 0. Okay, so this is an experiment in which we have obtain and foregone payoff. We tell them what the payoff of the 2 keys. Later I will tell you about experiment in which the payoff is limited for only selected key. So I want to go quickly over what I think are the most important results we found in this kind of line of research. And then this is first trial, and then second trial you select again and you get another feedback. And the typical experiments last about 100 trials, sometimes 500 trials. So here are the main results. So the result shows that people often learn to maximize, But they learn to maximize, but not always. There are robust deviation from maximization even under this really simple situation in which you get correct and immediate and full feedback after each trial. A particular large and robust deviation from maximization occurs when the best option on average is worst most of the time. And here are two examples. In problem one key give a bad gamble that provide a loss of 10 in 10% of the trials and a gain of 1 in the other 90% of the trial. So the expected value is minus 0.1. And the payoff, by the way, are in shekels. Like 3.5 shekels is $1. The other key always gives 0. Okay, so this is a very simple experiment. So this gamble is a bad gamble, has negative expected value, and this one gives 0. And what we see here, proportion of trials in which the subject selects a bad gamble, takes the risky, the action rate, selects the action over the status quo. And what we see is that in the first block of 20 trials, they selected the bad gamble 20% of the time, and then they learned to go down to 60%, but that was stable. And even if you run the experiment for 500 tries, they get stuck in 60% selecting the bad gamble. Okay, so this is one phenomenon, one experiment. You could say, well, this is because this is boring to select the 0 all the time, so they select the other key. But here we get the opposite phenomenon. Now the gamble is good. It's 10% of the time, minus 1 otherwise, positive expected value, or 0. So if people don't want the boring 0, now this is more interesting and maximize expected value. But they select it only 30% of the time. So they don't learn to maximize in this problem either. The two problems has a common thing, of course. In both of them, they behave as if they're underweight rare event, or behave as if they believe that it won't happen to me. As if the 10% event is too rare, and they think it's not going to happen. Okay, although they have 500 trials, so it's already, and there's no problem with foregone payoff. They see that it's happened 10% of the time, but they behave as if they think it's going to happen less. Their deviation from maximization as if they think it's going to happen less. Okay, this is one phenomenon. Question about this phenomenon? We tested this phenomenon in many settings, and it's extremely robust. I have to admit that I was surprised to see how robust it is. We find it in signal detection tasks, in a repeated decision with limited feedback. So when they don't have foregone payoff, we still get this phenomenon. We study it in one-shot decision, which they have 2 decks of cards. They can sample as much as they want, and then select once. They still behave as if they're underweight rare event. We get it in different culture. Actually, one experiment we run right here, and there's little difference between the Technion student and the student in Denmark, in this university. Very similar. We find a little bit different pattern in Taiwan, but not in the aggregate choice rate. The difference was that the Danish and the Israeli student look for sophisticated patterns, and the Taiwanese were more interested, behave as if they believe what happened the last trial will happen, do best apply to the last trial. So Danish and Israelis appear more to reflect less positive recency effect than Taiwanese in this experiment. This was with David and Sabila. We find it studying bees behavior, Israeli bees in this case, but
probably not different than Taiwanese.
Yeah. Actually, when we ran this experiment, there was a big problem in Israel that there was a group of Thai bees that come with some boat to Jordan and were about to invade Israel. And my co-author had to fight them. So there is some difference. There are smaller bees and they don't help the flowers, the oranges. We find it again with David and Sabila with decision among defaults. We find it also when we get both description and experience. And it was also found in decision for description. In fact, this is what Nassim Taleb called the black swan effect. Okay, so he cited us as a one justification for his effect, but he was smarter than us in investing wise. Notice that this phenomenon is exactly the opposite of what we know from prospect theory, because in prospect theory explains the coexistence of people buying insurance and lotteries as overweighting of error event. My research with Davide tried to explain why is this difference, what is the reason for the difference between the prospect theory phenomena and this phenomena. But this phenomena is really robust. Another robust phenomena is observed when you look at the effect of variability. In this problem, problem 3, is a trivial problem. One key always gives 1, the other one always gives 0. And after 100 trials with complete feedback, subject learned to select 1 95% of the time. So this is a nice example. But if you now add variance to the key with expected value of 1, and now it's provide 11 or minus 9 with equal probability, proportion of selecting go down to 55%. So in this case, variability reduces the attractiveness of the action. Now it's the opposite. Here we have number 4, minus 1 or 0, subject learned to select the 0. Now if you add variance to the minus 1, it's increased the choice rate to 45%. And basically this explanation was known to psychologists is what is called the pair variability effect. Just increasing variability moves choice behavior toward random choice. So it's another robust phenomenon. I would like to argue, or want to show you, that all these results and many other results that we got can be captured with a very simple model that basically says that what the subjects are doing, they behave as if, this is not a cognitive model, but I guess I'm safe here, and used to talk to psychologists who think that everything happens in the brain exactly, as if they rely on small samples. If you rely on small samples, about 5 past observations, all the results that we observe are accurate. Let me show you why. Think about this gamble, for example, and suppose I take sample of 5. So one key always gives 0. This is selecting 0 for sure, or this gamble. So if I take sample of 5, most sample of 5 will look like that. Because the rare event only happens 10% of the time. So if you take a sample of 5, the probability that it will include the minus 10 event is only 38%. So 62% of the sample of 5 will not include the rare event, and the bad gamble will look as if it's better. So if you rely on small sample, you will select the bad gamble 62% of the time, which is more or less what the subject did. And this is not only in this problem. If you look at all the 6 problems I've shown you, there is very high correlation between what people do and the prediction of this sample of 5 model. Very simple model captures those results really well. Okay, now the question is, why do people behave as if they rely on small samples? And one explanation that psychologists like, they say, well, it's cognitive limitation. We think that cognitive limitation could contribute it, but there is another reason. To show the other reason, consider a variant of this experiment that I've just shown you. But now, each trial starts with a trial number and a color. And these are the results. First 3 trials are yellow, and you get -1 from this key and 0 from here. Number 4, and try number 4, after you saw the pink, you got +2 from top, 0 from bottom. What would you, and this is the rest, what would you do in trial 16? Would you select top or bottom? Most subjects in this case would select top. That is, behave as if they rely on only 3 past experience, not on all 15. Because if you look at all 15, top is not good. But they notice some pattern. If pink, then you get something else. So when you see a pink trial, you only look at past experience under pink trial. Now when you run this experiment without colors, you still get the same thing. But probably the same reason, because they notice that every time after 3 minuses, a +1 is coming. So here again, they think that a +2 is coming. So basically what we think is happening is that subjects are looking for patterns. And they even look for pattern here. They had only one experience with +2, and they expect already here to get another +2. We argue this is something innate, and maybe a result of the fact that this is how we do for reading. To read well, you have to look for patterns. And maybe they do something like that. So this is one contributor. Of course, cognitive limitation could be another contributor. But notice that this computation for looking for patterns requires really to write a computer program that do that, it's really, you have to be good programmer. So this is not one of the simple heuristics that makes us smart. This is a complex heuristic that makes us smart if the environment is dynamic and there is pattern, but when the environment is static, make us deviate from maximization.
Sorry, can I ask
Yeah.
It seems that to find patterns you need to rely actually on very large samples.
Exactly.
Not small.
Yes.
So it's the opposite they're looking for.
No. What they say is that they basically our favorite model nowadays, that they rely on very large samples, do very complex computation. This is step number one. Step number two, they select all the past experience that seem similar to the current trial and rely only on them. So the final decision is if you rely on small samples, but this is after very complex cognitive computation that use very large samples and look at the correlation and the data. And this model approximates the optimal strategy if the environment is a Markov chain. But if but the environment is static, this is lead to deviation to behavior as if you underweight your error. This is exactly the story. Yes.
Yeah, but on the other hand, one could say, for instance, looking at the pattern, I would say there is no uncertainty here. It's not. I would say there is no looking at the pattern you showed before.
Yeah.
One could say it's totally deterministic.
Yeah.
There is no uncertainty.
This is exactly this is our story. We think that. By the way, this is exactly what the subjects think. Even when the environment is static, is static, they see pattern everywhere.
Yeah.
This is exactly our point. So the brain finds patterns when they exist, find it really well. Thanks to that we can read, but it also finds patterns when they do not exist. And this makes us behave as if we rely on small samples. But this is not because people are stupid. This is because they're smart. But when the environment is static and random, this leads to some deviation from maximization. Now my interest is not in finding the deviation. My interest is in finding how to create an environment in which people will maximize, and to use that for mechanism design. Let me show you another example. This one we call big eyes effect, sounds better in Hebrew. Here it's a simulated stock market. You have one stock that gives you a draw from a normal distribution with large standard deviation. Another stock also gives you a draw from a normal distribution with a mean of 0 and large standard deviation. And the index fund that gives you the average of the first two stocks plus some bonus. So this option, number 3, the index fund, maximize expected value and also minimize variance, and if you're loss averse, you also should prefer. And these are the results. In the first trial, they are indifferent. We actually tell them the pair of distribution in this experiment. This is a technique student. Initial trial, they behave randomly, and with experience, they reduce the proportion of selecting M. And what is the explanation for that? One explanation actually, that Goldstein told me that his wife, his mother, who was an important banker, told him as a joke, said, never invest in index fund. No matter what happens, you lose. Because index fund is never the best. You know, it's an average of 2. So go for one of the stocks you're doing, you have some chances to win. Index fund, you're always in the middle. You're always not the best. And this is basically consistent with our model. Because if you rely on small sample and do what works in this sample, the probability that the index fund will be better is very close to 0. Only if the two stocks are very close to each other is index fund the best. Okay, so this is derived from this phenomena that lead to underdiversification. It's one explanation for underdiversification in the stock market. And can also be explained by this story. Now, if we run the same experiment, but this time don't give them complete feedback. Only give them feedback about what they have selected. Now you get higher maximization. You give less perf and maximization go up. And the explanation for that is a hot stove effect that Yerker here has explained to me. And basically the story is that if you only get perf for what you selected, you select one of the stocks initially, you are happy, but after a sequence of bad outcomes, you say, oh, this is not good. You move to the second stock, you remember the first one is bad, you're happy, but then you have a sequence of bad outcome. You stop it and go to the index fund. Now it's never going to be as bad as this guys. You remember them as bad. And Yerker and G. March noticed that Mark Twain wrote about that in discussing his cats. So you guys know that. So if the cat jumps on the stove and gets burnt, he doesn't jump anymore and remember it as thought. So this is another robust phenomena. And the main difference between the result I've shown you when you have full feedback and the result when you don't have feedback is that no feedback increase basically triggers a hot stove. This is closer to your research. What happens when you have multiple keys and you don't have foregone payoff? So basically we study, and this is with my ex-student Kineta Duresco, we study these two situations. In one experiment, now they have many keys, each one of them is a key, they select on it and get some payoff. And they don't get foregone payoff. Now we create an environment in which there is rare disaster. When they select a key that are already selected in the past, they always get 0. If they explore, that is try a different key, they lose 10 in 10% of these keys gives them to a loss of 10, and 90% they get +1, so the expected value is negative, so this is a bad environment. In this environment there is rare treasure. 10% of the keys, if you try them first time, lead you to a payoff of 10, the other 90% to loss of 1. And what we get here is very similar to what we found in the 2 keys settings. This is a proportion of people selecting the exploration. So in the bad environment in which exploration leads to losses, people explore too much. And in this setting, they don't explore enough. So we get the coexistence of over and under exploration in this paradigm as well. As it turned out, only after we studied that, we realized that Dan studies a very similar problem. And I'll try to explain now the explanation to Dan's research. This result can be captured with an extension of the reliance on small samples model by assuming a two-stage choice process. Basically, the first stage, the agent chooses whether to explore, partially based on a small sample. So if I explore in the past, it was successful, I'm more likely to explore again. I think that Dan called that in one of his papers, maybe it's Gavati and Leventhal called it backward-looking exploration. And so this is basically the story. So when most time so you basically the decision whether to explore is similar to the decision I presented before. It's based on a small samples. In addition to fit this data well, and this is a model with 2 parameters that fit this data well, basically what you have to assume that the 2 parameters model, one of them is initial tendency to explore. I think that Dan called that forward-looking exploration. And so initially you have a tendency to explore, but with experience, your decision of whether to explore is more dependent of how fun it was to explore in the past. So this is that story. Let me try to clarify the relationship to Kahneman and Tversky's research. So Kahneman and Tversky, classical study, focus on decision from description. In the original problem, people were asked, what do you prefer, 5 for sure or 5,000 with probability 1 in 1,000, 0 otherwise? Most people prefer the gamble. This was to them a replication of the observation that many people buy lotteries. In this case, what would you prefer? -5 with certainty or -5,000 probability 1 in 1,000? Most people prefer the sure thing. This for them was a replication of the phenomena that many people buy insurance. We get the exact opposite. This is a proportion of choices consistent with overweighting of rare event. In their experience, most people overweight rare event. In our experience, most people underweight rare event. One explanation is that this is just different numbers. Maybe in the thousands you get overweighting, and in these small numbers you get underweighting, but this is not the case. Many other studies have shown that you get it with the same numbers. For example, in one experiment by Lacharaga and Gonzalez, subjects were asked to select between 3 for sure and 64 with probability 1 in 20. And the experiment was run for 100 trials with immediate feedback and full description of the curve distribution. In the first trials, they got a little bit behavior that could be consistent with overweighting of rare event, as in Kahneman and Tversky. But after 10 trials, behavior changes, and in the last 20 trials, people deviate in the direction of underweighting of rare event. So overweighting of rare event you get initially, but once people get experience, they behave as if they exhibit the opposite phenomena. In a paper with Davide, we show that this pattern can be captured with a simple model that assumes that when the subject see a description, they never, basically our model assumes they never trust the description. The description only reminds them past experience which they saw description like that. And that leads them to move the fact that you cannot trust anyone. If someone tells you 5%, it could be 5%, it could be something else. So it moves you towards the 50-50. And so initially, you rely on past experience before the beginning of the experiment, and which leads you towards the 50-50. But once you experience the current distribution, this bias is less, but you still rely on small samples, and this leads to the underweighting of error. This is the explanation. Let me now say a few words about applications. As I already suggested, we believe that even this limited phenomena, that is, basically there are really two phenomena here. One is reliance on small samples that lead to underweighting of error, and the hot stove effect. Which I think are the two most important phenomena that were documented in the study of learning. And part of my confidence that these are two the most important one is that we organize two international choice prediction competitions. We run the randomly selected gambles and we challenge people to predict the results. We organize two competitions like that, and models that capture these two phenomena was the winner in both cases. Some little difference between the quantification, but these are the two most robust phenomena. And I would like to convince you now that these two, understanding of these two phenomena is sufficient, have many important applications. And I want to distinguish between four applications. First class, just include simple deviation from maximization. Just the fact that people are not sensitive enough to rare event implies that sometimes we need regulation to force them to do the right thing. And this is very different than what the nudge literature nowadays suggests. In the nudge, you just nudge people to do the right thing. We suggest that sometimes you have to force people to do the right thing. You know, using economic incentive is useful. For example, take a professor like me and nudge him to take his car to inspections. My wife tells me all the time to do that. I never do it. But if I cannot drive with my car, if I don't take it to inspection once a year, I take it to inspection. So I think it's a very good idea from the government to force people to take car to inspection. The fact that you know that it's good for you, it's safer for you, it saves you money, and it can save your life to take your car to the garage is not enough to convince a common professor to do it. So you have to force it. I think, by the way, I'm a little bit of Bolshevik in that case. I think that it's probably good to people like me to force them to go to see the doctor once a year as well, to get a stamp. Because I say I go to the doctor all the time. We actually use that in factories, try to improve people obeying the safety rules. And the typical Israeli factory, the rule is that if you violate safety rules, if you don't use eye protection, for example, there is 700 shekels fine, that's about $200. And still, when we come to these factories, we find that most of the time workers don't do that. And of course, management don't give this punishment because no supervisor wants to fight with a worker and give him such a large fine. So what we did was just to propose to use a gentle fine. We basically gave the workers some lottery ticket. Each one of them was worth 10 cents. And we said that each time you do the wrong thing, the supervisor will have to take one of those lotteries. Okay, so very minor punishment. And that's improved safety in 11 factories go up. By the way, I noticed that in Denmark, you of course use this method. You don't have to learn from me. I was really impressed by taking the train here in Denmark. I took the train 3 times in the last 2 days, and every time there is someone asked for my ticket. So I assume that the punishment must be very low, but the probability of detection is 100% in my sample, relative to other countries. I think this is a nice trick, and this is more or less what we did. So basically implement the Danish train method in Israeli factories, and then it makes the Israeli Mediterranean workers behave like Danes, I think. At least in terms of using the eye protection. Another type of application is the fact that sometimes learning is very slow. And one example for that is the difference between first price and second price auction. The current model predicts fast learning in second price auction and slow learning in first price auction. And the reason is that in the first price auction, if the person who bids the most wins, if you bid the optimal bid for you, you're always sorry. Because, oh, I could bid a little bit lower and just an epsilon above the second bidder. Whereas in second price auction, you are never, if you bid the optimal bid, you're never sorry. So learning is faster. So this is a reason why second price auction explanation appear to work better. The new Middle East, we haven't solved that problem yet. But one of the problems is that Shimon Peres, when he was prime minister, says we have to. It's very easy to solve the problem in the Middle East. We just have to do it economically, to make sure that a young Palestinian boy, when he's born, will have a better future. He can be a computer programmer or a professor and doesn't have to fight for his future. And Israelis tried, and he was able to convince Israeli public for 2 months, but after 2 months there was still some terrorist attack and he lost power. My point is that the public learn very slowly. You know, it takes time for the potential terrorists to stop being terrorists, and it also takes time to the Israeli public to learn this is the optimal strategy. We give up. My argument that many political problems because people give up too early. They have the good idea, but learning is too slow. Other type of problem occur because there's convergence to inefficient self-confirming equilibrium. The best example, which is consistent with Yerker's research and with the hot stove effect, is the use of corporal punishment. Until very recent, and actually it started in Sweden, I think, that corporal punishment was banned in 1920. Until very recent, in some country, part of the world, in some places there still, if a student made a mistake in his homework, he would be beaten by the teacher. And Skinner, B.F. Skinner, the most important psychologist in my mind, was very effective in explaining people that this is a stupid strategy. Punishment are really stupid thing in this setting. When the agent have more than 2 alternatives, punishment can be very ineffective because you're not sure what the student will learn. For example, if someone is being beaten at school, he can learn not to come to school anymore. So that it will be a bad self-conforming equilibrium. He doesn't come to school, he's happy, but he destroyed his life. And our society is destroyed. So I think this was a very wise, one of the most important contributions of psychologists to the world is to convince people to ban corporal punishment. Depression has a similar explanation, but I don't think I have time to tell you about clinical psychology, but the common explanation of depression is similar to that. One thing that we recently implemented is dinners and conferences. Many times you go to conferences with the hope to meet new people, but then you're too lazy and you go to eat with your old friend, which is nice, but after 20 conferences, you heard the same story again, you say, oh, I should have tried harder. But this is a type of self-confirming equilibrium. If everybody else go to eat with your friend and you try to go for other people, you stay alone and may get even to your most boring friend. In a recent conference that we organized, with Reinhard Zelten, we organized auctions so the invited speaker, all the participants could auction how much they're willing to pay to go out with the invited speaker. That was important, we didn't make money out of that. But that was a big success. You know, what the invited speaker who initially didn't like to be auctioned said that they really had fun. And this, they may have to write some recommendation later in the future. That's okay. Last type of application is convergence to inefficient Nash equilibrium. For example, cheating in exam. When in the Technion they had the rule that in the beginning of each exam the proctors have to prepare a map of the location of all the students, so the teacher will know who are the people who cheated, and by looking at the correlation between the mistake, and then we're going to throw them out of school. Now, of course, this is Technion, and I'm there now for more than 20 years. I'm yet to look at any of those maps. And what happened that in the beginning of the exam, the proctor were busy in preparing the map, and then students would start talking. By the time the proctor would look at the class, they have nothing to do because it becomes a norm. If you ask someone not to talk, you say, I just asked my friend not to talk himself. So what we did was to delay the preparation of the map. And that was enough to reduce cheating. Because what the proctor do naturally is what they do in the training in Denmark. They see the first person moving their head, they ask him to come to the first row, and soon enough no one wants to move their head. Okay, you get to the efficient, in this case efficient, in my mind, equilibrium. Okay, and here's my summary. I try to convince you that the maximization assumption is useful but wrong. Mainstream tried to address this observation by adding parameters that imply keeping a weak version of the maximization assumption. The problem with that, I didn't criticize this literature here so much, but they have too many parameters. To me, even Bernoulli had too many parameters. Expected utility, I'm yet to see how economists use expected utility theory, because the parameter change from situation to situation. So not, of course, if you try to use prospect theory with 5 parameters, good luck, that change from situation to situation. So you really cannot do very much. Even this gentle, I'm trying to argue that even this gentle refinement are overfitting the data. So the solution that we propose, and as I said, I understand that many of you do something similar, trying to study learning process as an alternative approach. It focuses on the study of the decision from experience in an attempt to understand the condition under which people behave as if they maximize expected return. And we argue that the useful inventions use similar logic. They realized when people learn to maximize, realized by exploration or by chance, but they created a situation in which the maximization assumption works, and for that reason, this is a stable situation, it's effective. And I hope that now that if we understand this thing better, we create more situations like that will help us create a better world. So this is my story.